So anyway, so what is the effect of frequency? So the frequency has a wavelength. Every signal has a frequency and a wavelength. They're related. Low frequency means large wavelength. So it's just think about it. Low frequency means a very tall person. Okay? It can go farther. Low frequencies can go very, very far. They can go 45 miles. The high frequencies have very low bandwidth. They are tiny people. They can't go 45 miles. They can't even go 100 meters sometimes, depending upon the frequency. So everything is related to the wave. OFDM. Right. So the question you're asking is, why do we use high frequency at all? The question is because we don't have low frequency. That's the answer. And I will tell you, basically that's what is happening. So the whole world in the beginning, it started with the lowest frequency possible. So most of this communication was at 1 megahertz, 2 megahertz, 30 megahertz. When we nothing left, then we went to 40, 50, 60, 100, 200, 300. Kept on moving. 2 gigahertz. When the gigahertz, nothing was left, then they moved to 2 gigahertz, 4 gigahertz, 5 gigahertz. Now there's nothing left, so we are going to terahertz. We are just using unreclaimed space. Unclaimed space. Right? So terahertz is not our first choice, but that's what is available. And this slide will bring out some other points. But the first point is higher frequencies have higher attenuation. So the higher the frequency, means this lower the wavelength, they go down fast. Okay? And now that is advantageous and that is disadvantageous. One disadvantage is that if you wanted to do a television broadcast, you couldn't do at gigahertz, because if you did at gigahertz, all the neighbors will have to be able to listen, but the people in the server will not be able to get your TV. Because gigahertz doesn't go that far. So television traditionally have been at 700 megahertz for that reason, because that can go 45 miles, and that's where they want to be able to at least go that far. All right. Cellular people said, okay, all right, I don't want to go to 45 miles. I can go less. So they were given above 1 gigahertz because they can cover. And now they're okay. Does anybody know what is the relationship between the frequency and the attenuation? We discussed this one. So if anybody remembers it will be good. So there was a formula where we talked about the received power is equal to transmitted power times something, and there was an F somewhere in that formula. And there was a D in there, there was a lambda in there, D, lambda. If you remember any of that part of that formula, anybody remembers that formula? For D, for power of D was 4. We started with 2 and then we said, no, it is actually 4. But F is squared. So basically it was lambda squared, right? So it is a squared power, not exponential. All right. So 18 gigahertz has 20 dB more than 1.8. You see the ratio is 10. And therefore 10 is equal to 10 dB right there, plus twice, because it is squared, it is 20 dB. And then higher frequencies need a smaller antenna. Now that's another thing, is that the size of the antenna is actually, ideal size is lambda by 2. So for this frequency you need big antennas, like we used to have on for the television outside our house, big antenna. And so that's not very good for cellular people. They don't want you to carry around that big antenna, with you in your car. So they are happy with something which is higher frequency, which goes shorter distance. Higher frequencies are affected more by weather. So the higher the frequency, more they are affected by rain and everything else. And there are other things such as oxygen molecules and so on and so forth. So lower is better. And if you go over something, then then you have to worry about what happens at this particular frequency. There might be some other natural phenomena that can affect that. So, and it's not like a straight line like this. It is sometimes like this. And people select wherever the least interference is. So there are many frequencies which are not used simply because there is a lot of things happening in the world because of natural things that affect. So oxygen molecule is one of them. High frequencies have more bandwidth and higher data rate. Now, here's the thing. If you go into 30 megahertz, all I can give you is 1 megahertz. I can't give you 40 gigahertz there at 30 megahertz, right? But if you go at 60 gigahertz, I can give you 2 gigahertz. Right? So you can get a lot of bandwidth at high frequencies, But at the low frequencies, the available bandwidth is very low. Right? So that is why they are moving to high frequencies, is because now at 60 gigahertz, I can use 6 gigahertz and nobody will complain. Right? And I can get 6 gigabits by just doing BPSK. Right? Whereas to get 6 gigabit at low frequencies, I will have to use really sophisticated coding to get that. So high frequencies are good for high throughput. High frequencies allow more frequency reuse. Now all of this has been compiled. I had compiled this from many different places. This is slide, right? And at one place I'm presenting it to you. So please remember, this is all, very, it's not just available any place I have seen at one chapter or one slide, okay? So high frequencies allow more frequency reuse, means because they don't go very far. Let's say I have very high frequency which goes 10 meters, then I can use the same frequency again at another 10 meters. Every 10 meters I can use the same frequency. On the other hand, if it goes to 45 miles, I can't use that frequency for 45 miles. So not going far is good, because now I can reuse it again and again. And they attenuate close to cell boundaries, and low frequencies propagate very far, so you can't do that. OFD, effect of frequencies. Low frequencies have, we already said that. That means we have longer cell radius, right? The television channels are used only for the whole city. You can't use the same frequency again in the same city, which is good for the rural areas. A smaller number of towers, which is good, and longer battery life, because longer battery life basically because the frequency goes very fast. So to send from from cell phone a kilometer, you need a lot of power at high frequency. At low frequency, even at low power, it goes very far because there's less attenuation. So power is less. It's good. Battery life is good. All right. So lower frequencies require larger antenna and antenna spacing. So if you start using multiple antennas, which I will come in the next slide, then not only the size of the antenna, you see this one, the size of the antenna is larger for the low frequency, right? But also the distance between the antennas has to be larger, right? If you have two antennas, you can't just put them like close to each other. They have to be, again, lambda by some number, 4 or 2 or something like that. So MIMO is difficult. Multiple antenna is difficult. Low frequencies have a smaller channel width, which we talked about, and therefore need aggressive MCS. MCS means modulation coding. Modulation and coding is, you need 256 QAM or 1024 QAM. At high frequencies, you can just be happy with BPS. Doppler shift is V times F upon C. High frequencies have high Doppler spread. You see, V times F upon C. So it is proportional. The Doppler shift is proportional to the frequency, and therefore low Doppler spread at lower frequency. So they are good that way. For you can go at high speed and still not have that much of Doppler shift. And therefore you cannot use 60 gigahertz for mobility. You cannot be driving in a car and be using 60 gigahertz. So people have said in practice, for mobile applications, for cellular application, we need to keep below 10 gigahertz. No, because there is only so much available. 30 megahertz, you can't give more than 30 megahertz. At 60 gigahertz, I can give you 6 gigahertz. At higher frequencies, there is so much band. At lower frequencies, there is only so much band. At 30 megahertz, how much can I give you max?
30 gigahertz?
Megahertz.
Oh,
there is a carrier frequency, right? And that could be 60 cycles for the electric current, could be some megahertz for some transmission, and so, or it could be gigahertz, or it could be terahertz. So there is a continuum of frequencies, and there was this chart I had shown in the previous module where we showed you what are the different frequencies used for. You remember that chart, spectrum allocation? You remember that one? Huh? So at low frequencies, the total available is low simply because they are low. At 30 megahertz, I can't give you, at 30 megahertz, 0, 30, and 60, 90. Now at 30, how much can I give you? I cannot give you 30 to 330. Whereas at 3 gigahertz, I can give you 3 gigahertz and nobody will notice because you'll get 3 to 6 gigahertz. That's the end of this module. And path loss increases at a power of 2 to 5.5 with distance. So we saw this actually in this module. We had d raised to 4 law, and we said that the d power is not really fixed. D square can be shown by that 2-ray model, but really it could be 4 is more common. They measured it in the cities and they found that the power of 4 is kind of. Fading means changes in the power, changes in, as the position, you change the position. As you change the position, the power received changes, and there was this weird graph which was along a line. First it goes down by the line, but then it also along the line there is a sinusoidal variation. Around the sinusoidal variation there is a little sinusoidal variation. Remember that graph? That one is basically fading. Fresnel zones is the idea that whenever you have two antennas, the communication takes place in Fresnel zones, and if there is obstruction in the Fresnel zones, then the signal reduces significantly. So your antenna has to be at least one such that the first Fresnel zone is above the ground, doesn't touch the ground. So that ellipse that we had drawn, those ellipses have to be, because if you put them too low to the ground, then Fresnel zone touches the ground. Multiple antennas, and we talked about receiver diversity, transmit diversity, smart antennas, and MIMOs we talked about. And then the OFDM basically splits the band into many orthogonal frequencies, and then you can do both FDMA and TDMA together at the same time in OFDM. You can divide by frequency and time, and you can really put any squares anywhere, any size. So that's a good question. What is the difference between subcarriers and a carrier? They are one and the same. If we use one carrier, then we call it a carrier. If we use OFDM, then we use thousands of them for the same same space, and we call them subcarrier. So these, for example, these are subcarriers. But if we were to use this whole thing in one thing, it will be called carrier. Now, having said that, I mean, when we are talking about this subcarrier and we are talking about its modulation, then we might even call it a carrier, because each subcarrier is a carrier. It is carrying something, right? Except that it is a part of a big group, so we call it a subcarrier, right? But each carrier, each of the subcarrier is a carrier. Okay, yeah, good question. So what is the size of FFT? So FFT generally come in power of 2. So if you take 1,000 carriers, subcarriers, then you will need a FFT which can do 1024. Okay, which is the power of 2. If you do, let's say, 1025, then you mostly likely need 2048 FFT. So the FFTs only come in powers of 2, so 2 raised to 10, 11, 12, 13, 14, like that you go. And so you select the closest one, FFT chip, or whatever you want to do, right? So they don't come in odd numbers or any other numbers. Yeah. So what happens is whenever you transmit a signal, you're not transmitting sine waves. If you just transmit one sine wave in the frequency domain, it will just look like a pulse, right? If you transmit a square wave, right, then a square wave is not sine. So what will happen is you can express a square wave as a series of sine waves, many sine waves, one here, one little there, one little there, one little there, with a different amplitude, right? So the power spectrum looks more like this than a impulse on the frequency domain. Now this is the frequency domain, frequency on the horizontal axis.
That's what square waves would sort of look like?
Square waves will look, even weirder than this, but that's what, yeah. So this is basically saying that the power is not equally distributed, is not just at one frequency, it is, kind of at the frequency you want plus a little bit more around it. So the frequency spectrum of any signal, any transmission is like this. Basically, it is not smooth like this. It could be very weird like that. So it goes into the neighboring places. And all the licensing requires that you limit your transmission into neighboring places as much as you can. So when they give you a frequency band, they say this is your band and no more than 5% overflow into the neighbor or whatever, right?
Is this something that can be improved?
Of course, the more money you put it, you can just put a filter and then nothing will go beyond that. Yeah. Yeah, right. That's what 1024 is. So basically, that's another thing is that why you cannot have 250, 2048 is because you need lots of filters of that kind, little tiny, to make sure that nothing overflows into each other. You need modulators which are very precise, which are very good. You need circuits that do not have any noise. Homework 4. I think you have all submitted one today. Homework 4A. Did you get all of them? Okay. So 4B and C are now due. B is given the subcarrier spacing and the channel bandwidth. It should be trivial now, given the examples I've given. You can find out how many carriers and what is the FFT. In a scalable FDMA system, now in the scalable one, you basically what you do is, given upon the channel 10 megahertz is 1024. Now you can see what will be for 1.25 megahertz, 5 megahertz, and 8.75 megahertz. How many carriers, and then you could think about also how many what size FFT you will need. Although in most of these systems, I don't think they change the FFT size. They probably sell the same cell phone in all the countries. You just don't use that many subcarriers in some countries. Right? The idea of scalable is so that you go to different countries and they have a different size of the band. The rest of the logic works.